Something impossible just happened. And if you're hearing about this anywhere else, you're already too late. Because what the James Webb Space Telescope captured 3 days ago isn't just another blurry dot in space. It's the first time in human history we've seen the surface of another world with enough clarity to say, this could be home. Not an artist's rendering, not a simulation, not a composite image stitched together from data, a real photograph of a real planet orbiting a real star. And when scientists saw what was in that image, some of them stopped talking mid-sentence. For over a decade, we've been told that seeing exoplanets directly is nearly impossible. The light from their stars drowns them out. The distances are too vast. The technology isn't ready. And yet, Webb just did it. And the world it revealed is so disturbingly similar to Earth that the first question scientists asked wasn't, is this real? It was, how long has this been there? Because this discovery doesn't just prove we can see other worlds now, it suggests we've been surrounded by them the entire time, hidden in plain sight, waiting for us to build eyes sharp enough to finally look back. What Webb photographed is a planet called K2-18b. And if that name sounds familiar, it should. This is the same world that shocked astronomers last year when Webb detected something in its atmosphere that shouldn't be there, dimethyl sulfide, a gas that on Earth is only produced by living organisms. At the time, scientists were cautious. Atmospheric data can be misleading. Chemical signatures can have non-biological explanations. But now, Webb has given us something far more difficult to dismiss: visual confirmation of what lies beneath that atmosphere. And it's an ocean, not a small sea, not isolated lakes, a planet-wide ocean so deep that if you stood on its surface, you wouldn't see land in any direction, just water stretching endlessly toward a horizon lit by a dim red sun. The image itself is deceptively simple. A pale blue sphere hanging in the void, its surface mottled with swirling cloud patterns and darker regions that suggest depth. But what makes this photograph historically significant isn't what it shows, it's what it proves. For the first time, we are not inferring the existence of water on another world, we are looking at it. Think about that for a second. Every other exoplanet we've studied has been understood through indirect observation. We measure how starlight dims when a planet passes in front of it. We analyze the spectrum of light filtering through its atmosphere. We calculate mass, radius, and temperature using mathematical models. But we've never actually seen one, until now. Webb achieved this by using a technique so precise it borders on science fiction. The telescope didn't just point at K2-18b and snap a picture. It waited for months, tracking the planet's orbit with surgical timing. And when the alignment was perfect, when the planet was at its furthest point from its star, Webb used its coronagraph to block out the star's overwhelming light, allowing the faint reflection from the planet's surface to finally emerge. What appeared on the sensor was faint, almost ghostly, but it was there. A crescent of light reflecting off liquid water. And when that image was enhanced and processed, scientists saw something that made them recalculate everything they thought they knew about this world. The ocean wasn't calm, it was moving. Massive storm systems churned across its surface. Cloud formations the size of continents spiraled and dissolved in patterns eerily similar to Earth's own atmospheric dynamics. This wasn't a dead world covered in stagnant liquid. This was a planet with weather, with circulation, with active, ongoing processes that only happen when energy, water, and chemistry interact over time. And that's when the implications started to cascade. K2-18b is not in our solar system. It's not even close. It orbits a red dwarf star 120 light-years away in the constellation Leo. That's far enough that the light Webb captured left that planet during the early 1900s, back when humans were still figuring out how to fly. And yet, despite that distance, despite the differences in star type and planetary architecture, K2-18b looks recognizable. It looks like something we understand. But here's where it gets stranger. K2-18b is not an Earth twin. It's far larger, about 8.6 times Earth's mass. It has no solid surface the way we do. Instead, its ocean is thought to sit atop a thick layer of high-pressure ice, compressed by the immense weight of the water above it. Beneath that ice could be a rocky core, or it could be something else entirely. We don't know yet, but what we do know is that this architecture, a deep ocean, a thick hydrogen-rich atmosphere, internal heat from gravitational compression, creates exactly the kind of stable, protected environment where chemistry doesn't just happen, it accelerates. On Earth, life began in the ocean, not on the surface, but deep underwater, near hydrothermal vents where heat and minerals mix with seawater to create the first organic molecules. Scientists have long theorized that similar processes could occur on ocean worlds elsewhere, but until now it was just theory. Now, we're looking at a world where those conditions don't just exist, they dominate. And then there's the atmosphere. Last year, Webb detected methane, carbon dioxide, and traces of dimethyl sulfide in K2-18b sky. That combination is significant because it's chemically unbalanced. Methane and oxygen, for example, react with each other. They don't coexist naturally unless something is constantly replenishing them. On Earth, that something is life. Photosynthesis produces oxygen. Biological decay produces methane. Together, they create an atmospheric signature that screams biology from light years away. K2-18b has that signature, and now we have an image of the world producing it. This is where skepticism starts to fracture. One atmospheric anomaly can be explained away. 2 is suspicious. 3 starts to look like a pattern. But a planet-wide ocean, active weather systems, chemical imbalances, and now direct visual confirmation. At some point, the burden of proof shifts. It stops being about proving life exists and starts being about proving it doesn't. And so far, no one has been able to do that. What makes this moment even more unsettling is the speed at which our understanding is changing. Just 5 years ago, K2-18b was barely mentioned in scientific literature. It was cataloged, measured, and mostly ignored. Then, Webb launched, and within 2 years, this forgotten world went from irrelevant to the single most important exoplanet humanity has ever studied. But K2-18b isn't alone. Webb's success here has triggered a cascade of follow-up observations on dozens of other ocean worlds. Planets like TOI 270d, LHS 1140b, and GJ 1214b are now being re-examined with the same techniques. And early results suggest K2-18b is not an outlier. It's an example, a preview of what might be waiting on world after world after world. Imagine that for a moment. Imagine a universe where ocean planets aren't rare, where deep, stable, chemically active seas are as common as rocky planets or gas giants, where life doesn't need perfect Earth-like conditions, it just needs time, water, and energy. Webb is showing us that universe, and it's not theoretical anymore. Here's the part that no one is saying out loud yet, but everyone is thinking. If K2-18b has life, even microbial life, it would mean biology is not a fluke. It would mean the same chemical processes that ignited life on Earth 3.8 billion years ago are playing out right now on planets scattered across the galaxy, following the same rules, driven by the same physics. It would mean we are not special. We are not alone. We are not the universe's only experiment. We are one result among billions. And if that's true, then the question stops being, does life exist elsewhere, and becomes something far more immediate. How do we find it? Because Webb just proved we can see these worlds, we can photograph them, we can analyze their atmospheres in real time. The technology exists, the targets are identified, the only thing left is time. But time is accelerating. Right now, Webb is locked onto K2-18b for extended observation. Over the next year, it will track seasonal changes, study the composition of those massive storm systems, and search for additional chemical markers that might confirm biological activity. If dimethyl sulfide levels fluctuate in predictable patterns, if methane concentrations spike during certain orbital phases, if oxygen appears in concentrations that defy non-biological explanation, then we won't need to speculate anymore. We'll know. And that knowledge will arrive not through a distant signal, not through a decoded message, but through an image, a photograph of another world taken by a machine orbiting 1 million miles from Earth, capturing light that traveled for over a century just to reach us. This is what history looks like when it's happening. Not dramatic, not loud, just a gradual accumulation of evidence so overwhelming that denial becomes harder than acceptance. K2-18b is that accumulation, and the image Webb captured is the proof that we are no longer searching blindly. We are looking directly at the places where life could exist, and some of those places are looking back. But the story doesn't end with K2-18b, because while the world was fixating on that single ocean planet, Webb was quietly compiling a portfolio of candidates so compelling that the real revelation isn't one world, it's the pattern they form together. Consider what's happening right now in our own solar system. Ceres, the dwarf planet orbiting between Mars and Jupiter, was dismissed for decades as nothing more than a glorified asteroid. Webb changed that assessment overnight. Spectroscopic data revealed extensive salt deposits and hydrated minerals across its surface, the unmistakable chemical fingerprints of liquid water that once flowed, or perhaps still flows, beneath an icy crust. Follow-up analysis suggests a subsurface ocean larger than all of Earth's freshwater reserves combined, sealed away from radiation and cosmic impacts, creating conditions eerily similar to the lightless depths of Earth's oceans, where entire ecosystems thrive without ever seeing the sun. The parallel is uncomfortable. If life can flourish in Earth's deepest trenches, sustained by chemical energy from hydrothermal vents rather than sunlight, then Ceres offers the exact same blueprint: water, minerals, heat, stability, everything biology needs hidden just beneath our noses for the entire history of human astronomy. And Ceres is not alone. Beyond Neptune, in the frozen outer reaches of our solar system, gravitational anomalies have been whispering about something massive for years. Kuiper belt objects move in synchronized patterns, their orbits warped and aligned as if an invisible hand is guiding them. Scientists call this phantom world Planet 9. Calculations place it somewhere between 100 and 200 astronomical units from the Sun, so distant that sunlight reaching it would be barely distinguishable from starlight. But invisibility doesn't mean insignificance. If Planet 9 exists, it would be roughly Earth-sized, with enough internal heat from radioactive decay and gravitational compression to potentially sustain subsurface oceans for billions of years. A rogue planet, born elsewhere and captured by our sun's gravity, carrying with it the chemical history of wherever it came from. Webb's infrared sensitivity gives humanity its first realistic chance of detecting this ghost world directly. And if it's found, it would mean our solar system is far stranger, far more dynamic, and far less mapped than we ever assumed. But the real paradigm shift comes when you step outside our solar system and look at what Webb has revealed about worlds we thought we understood. 40 light-years away, the TRAPPIST-1 system hosts 7 Earth-sized planets packed so tightly around their ultra-cool red dwarf star that their orbits resemble a cosmic clockwork mechanism. What Webb revealed is not just diversity, but repetition. Not one potentially habitable world, but 3, possibly 4, each showing independent signs of atmospheres capable of retaining heat and moisture, each positioned at distances where liquid water could persist for billions of years. TRAPPIST-1e stands out as particularly compelling. Models suggest it maintains surface temperatures mild enough for global oceans, protected by an atmosphere thick enough to stabilize climate, but not so dense that greenhouse effects spiral out of control. Its neighbors, TRAPPIST-1f and 1g, may host water as well, vast reservoirs locked beneath icy shells, insulated from the star's occasional flares. Imagine standing on one of these worlds and looking up. Another Earth-sized planet hangs in the sky, close enough that you could see weather patterns shifting across its surface with your naked eye. Close enough that atmospheric exchanges between worlds might not just be possible, they might be inevitable. If life emerged on one of these planets, could it spread to the others? Could biology itself become a shared property of an entire star system rather than a single isolated world? TRAPPIST-1 shatters one of our deepest assumptions, that habitable planets are rare, isolated accidents. This system suggests the opposite, that once the right stellar conditions exist, nature doesn't produce one life-friendly world, it produces several, stacked side by side, each experimenting with different configurations of the same basic ingredients. And then there's Proxima Centauri b, the planet that refuses to be ignored, because it's so close it feels like destiny. Orbiting the nearest star to our Sun, just 4.2 light-years away, Proxima b sits squarely in the habitable zone of its red dwarf host. For years, scientists were skeptical. Proxima Centauri is violent, hurling powerful stellar flares toward its planets with unpredictable frequency. Any atmosphere should have been stripped away eons ago. Any surface water should have boiled off into space. But Webb's refined observations suggest Proxima b is tougher than anyone expected. Spectroscopic hints point toward the possible presence of a magnetic field, or an unusually dense atmosphere, some form of protective shield allowing the planet to endure conditions that would sterilize most worlds. If water exists there, it's likely underground, pooled in stable reservoirs shielded from the star's rage. What makes Proxima b so powerful in the search for life isn't perfection, it's proximity. Signals from this world take just over 4 years to reach Earth, a whisper across the cosmic void compared to the century-long silence from K2-18b, or the 4-decade journey from TRAPPIST-1. If we detect biosignatures here, even ambiguous ones, we could send probes. We could study it up close within a single human lifetime. And if life exists on a planet this hostile, this close, it would shatter the idea that biology requires gentle, Earth-like conditions. It would mean life is tougher, more adaptable, and far more widespread than we ever dared imagine. Now compare these worlds. Ceres hides its ocean beneath rock and ice. K2-18b buries its sea beneath a crushing hydrogen atmosphere. TRAPPIST-1's planets balance water on their surfaces or seal it away depending on their distance from the star. Proxima b survives by armoring itself against stellar violence. Different strategies, different architectures, same result. Environments where water, energy, and chemistry can interact over geological timescales. This is where the statistical argument becomes overwhelming. 1 ocean world is fascinating, 5 is a pattern, 10 forces a conclusion. When you line up Ceres, K2-18b, TRAPPIST-1e, Proxima b, LHS-1140b, TOI-700d, and GJ-1214b side by side, skepticism starts to collapse under its own weight. Each of these worlds satisfies different criteria for habitability. Some have thick atmospheres, others have thin ones. Some orbit calm stars, others endure violent ones. Some hide their oceans, others display them openly. But all of them, every single one, possesses the fundamental ingredients life requires, and all of them exist within a small corner of the galaxy we've barely begun to survey. Scale that up. The Milky Way contains an estimated 100 billion stars. Conservative estimates suggest at least 20 billion of those stars host Earth-sized planets in their habitable zones. If even a fraction of those planets follow the patterns Webb is revealing, if ocean worlds, subsurface reservoirs, and chemically active atmospheres are common rather than exceptional, then the number of potentially habitable environments in our galaxy alone climbs into the billions. Not millions, billions. And that's just one galaxy among trillions. At this scale, the question stops being could life exist elsewhere and becomes how could it not? The universe isn't hostile to biology. It's saturated with opportunities for it. Water is one of the most common molecules in the cosmos. Organic chemistry happens spontaneously wherever the right conditions exist. Energy sources, stellar radiation, tidal heating, radioactive decay, gravitational compression are abundant. The only rare ingredient is time. and the universe has had 13.8 billion years to experiment. What Webb reveals is that we are not searching for needles in a haystack. We are standing in a haystack made of needles, trying to figure out which ones to examine first. This realization carries weight that goes beyond science. For thousands of years, humanity built its identity around the assumption of cosmic solitude. We are special. We are unique. We are the universe's only conscious observers. Religions, philosophies, and entire frameworks of meaning rest on that foundation. Webb is eroding it, not with a single dramatic discovery, but with an accumulation of evidence so patient and relentless that denial becomes exhausting. Because here's what we know now. We know that ocean worlds are common. We know that thick atmospheres can protect life from hostile stars. We know that subsurface environments offer stability across billions of years. We know that the chemical building blocks of life are universal. And we know, thanks to K2-18b, that we can now photograph these worlds directly. The technology exists. The targets are identified. The observations are underway. What happens next is not a question of capability. It's a question of time. How long until Webb detects oxygen and methane coexisting in an atmosphere with no plausible non-biological explanation? How long until we photograph seasonal changes on an ocean world that match biological cycles? How long until we find chemical signatures so specific, so repetitive, so unmistakable that even the most hardened skeptics have to admit the obvious? Some scientists believe that moment is years away. Others think it's already happened, buried in data we haven't fully analyzed yet. Either way, the trajectory is clear. We are not moving away from the discovery of extraterrestrial life, we are accelerating toward it. And when it comes, not if, but when, it will not arrive as a headline or a press conference. It will arrive as a photograph, a spectrum, a graph showing chemical concentrations that rise and fall with planetary seasons. Data so mundane in its presentation that its revolutionary nature might take days to fully sink in. This is what history looks like in real time. Not explosive, not cinematic, just evidence accumulating quietly until the weight of it becomes undeniable. K2-18b is the beginning of that accumulation. The image Webb captured is proof that we are no longer guessing, we are observing. And what we're observing is a universe that looks less empty with every passing month. The photograph of K2-18b will be remembered not because it showed us an ocean on another world, but because it marked the moment humanity transitioned from wondering if we're alone to preparing for the confirmation that we're not. Because if one ocean world exists, then dozens do. And if dozens exist within the narrow slice of space Webb has surveyed, then thousands exist in the regions we haven't looked at yet. And if thousands of ocean worlds are scattered across the galaxy, then the idea that all of them are lifeless becomes statistically absurd. Life is not fragile. It's not rare. It's not dependent on a narrow set of Earth-like conditions. Webb is showing us that life is what happens when water, energy, and chemistry are given enough time to interact. And the universe is very, very good at providing those three things. So here we are, standing at the threshold of the most important discovery in human history. Not because we found definitive proof of alien life, but because we found definitive proof that the conditions for life are everywhere. The universe is not silent, it's patient. And it's been waiting for us to develop the technology to finally hear it. What comes next will define us, not as the species that found life, but as the species that was ready to accept what it means. Ready to understand that Earth is not the center of a biological miracle, it's one example among countless others. Ready to realize that the question humanity has asked for millennia is about to be answered. And the answer is already forming in the data, in the images, in the atmospheric readings streaming back from worlds we can now see with our own eyes. Stay with this. Watch the discoveries unfold. Follow the data as it arrives. Because the photograph Webb captured of K2-18b is not an ending. It's the first frame of a story humanity has been waiting to tell since the moment we first looked up at the stars and wondered if anyone was looking back. The answer is coming, and it's closer than we ever imagined.